This standard cognitive pipeline assumes sensory input enters left, passes through perception, triggers emotion, and arrives at higher cognition. It treats these as distinct processing stages, where raw data waits. But massive, continuous integration of thought quickly breaks this linear timeline apart. The Brain Kinematics Model, developed within continuity theory, proposes an entirely different architecture for how the mind organizes itself. In this framework, sensation, emotion, intuition, and cognition do not wait in a queue. They ignite simultaneously. The sequence we experience in thought is an illusion. It is caused by differing degrees of maturation across the network, not different times of initiation. Watch how a single pulse of sensory data instantly illuminates this entire topological network. It touches all functional domains at once, at a faint opacity. In those first milliseconds, these massive simultaneous activations exist only as primitive, highly unstable states of feeling and perception. To create a stable thought, cortical activity must continuously loop back on itself, pulling in new sensory evidence and retrieving internal memories with every pass. As these nodes pulse recursively, you can see the connections thickening. Each cycle progressively refines that initial primitive state into a coherent, organized cognition. Every mentation you experience is an act of continuous recursive balancing on what is called the regulatory continuum. This is the exact same biological mechanism that governs both flawless logic and severe psychiatric pathology. To understand how this works mechanically, we look at the biological substrate of the model, localized clusters of neurons called memory fractals, which are distributed across the cortex. This 3D model shows the first of two opposing kinematic forces driving thought. As internal regulatory strain rises, it triggers vertical recruitment, stacking and activating related layers of memory fractals within a single column. Vertical recruitment progressively activates these related memories, providing a developing thought with its necessary local stability. But stability requires context. The opposing, complementary force is horizontal propagation, where lateral waves of energy spread outward from those activated columns. Horizontal propagation reduces the effective resistance across the cortex. It bridges distinct networks so they can communicate, providing the thought with its required adaptability. Every recursive cycle of a thought demands a highly precise ratio of local stability from recruitment to distributed adaptability from propagation. The successful generation of any idea relies entirely on maintaining the dynamic tension between these localized and distributed forces. We can map these microscopic cortical forces onto a macro-level dynamical systems model. Look at this 3D attractor landscape. That glowing point of light entering the slope represents an emerging mentation. The goal of this regulatory continuum is convergence, successfully guiding the developing thought into a resolved, stable organization. In healthy mentation, this precise balance guides the thought smoothly down the topography, past dead ends, until it settles securely into a deep, stable valley. Reaching this stable valley is successful cognition. You recognize a face, solve a math equation, or recall a specific memory. However, this convergence is a biological tendency. It is not a guaranteed mathematical outcome. Because the brain relies on probability and tension, the exact same kinematic principles neatly model severe psychiatric failures when stability and adaptability lose balance. Here's the first alternative outcome: oscillatory or idle mentation. The point of light gets caught in a shallow depression, circling endlessly. The mechanical failure here is clear. Vertical recruitment repeatedly exceeds effective lateral integration. Stability overpowers adaptability, forcing the network to reactivate the exact same memory fractals over and over. Clinically, this trajectory directly correlates to rumination, the cycles of obsessive-compulsive disorder, and persistent intrusive thoughts. The second outcome is divergent mentation. The point of light rolls down, but immediately shatters into multiple smaller points that scatter into competing pathways. In this case, horizontal propagation heavily outweighs stability. The network continuously pulls in new associations before the old ones can consolidate. This divergent trajectory maps to distractibility, manic associations, and the disorganized thought patterns seen in schizophrenia.
It is worth noting that mild, non-pathological forms of this exact same divergence serve as the mechanical basis for creative ideation. In both conditions, the brain isn't broken. The regulatory state simply failed to find the optimal attractor basin.
The third outcome is premature collapse. Notice how the point of light simply dims and vanishes before reaching any stable basin. This happens when the regulatory signal entirely loses coherence. It occurs due to insufficient memory support, emotional overload, or physical fatigue. Clinically, we see this collapse as cognitive exhaustion. Finally, the fourth outcome, maladaptive stabilization. The thought settles decisively into a deep valley, but a label flags that this valley is misaligned with the actual sensory data. This represents a mechanical paradox. The regulatory dynamics successfully converged into a highly stable state, but the resulting cognitive representation is totally inaccurate to reality. This perfectly stable but demonstrably false topography forms the mechanical architecture of rigid delusions, severe cognitive biases, and persistent false beliefs. If these failed convergences cause such distress, we have to ask what causes the regulatory topography to warp in the first place. The model groups these disruptions into a strict hierarchy. This diagram shows biological abnormalities at the foundation, functional disturbances in the middle, and emergent mentation at the top. Notice the bidirectional arrows flowing both up and down. A foundational biological disruption, like neuroinflammation, vascular pathology, or neurodegeneration, physically alters the tissue of the regulatory continuum. In the middle layer, functional disturbances, like chronic stress, trauma, or maladaptive learning, warp the recruitment mechanics without physically destroying the tissue itself. These lower layers interact to permanently warp the top layer, emergent mentation, bending the topography to create the failed attractors we identify as mental disorders. Pathological thought and healthy thought utilize the exact same kinematic machinery. Disorders are simply altered trajectories within the exact same continuous regulatory space. The realization that consciousness is a dynamic, continuously organizing reality rather than a rigid sequence of mechanisms is not an entirely modern idea. Long before neuroimaging existed, classical philosophers mapped out this precise phenomenological landscape. Take a look at this marble bust of Aristotle. Figures ranging from Aristotle to the illuminationist Suhrawati and the metaphysician Mullasadra accurately described the recursive, intuitive nature of the mind using the language of phenomenology and metaphysics. Modern system science does not replace their work. It provides the biological vocabulary and mathematical topography to prove those early intuitions on a cellular level. The Brain Kinematics Model unifies these two eras of human thought. It demonstrates that humanity's collective effort to understand consciousness is a continuous, recursive evolution toward coherence.